Okay, I'm going to go through problem 144 from your textbook. And in doing so, I want to emphasize a process for solving problems and approaching problems. All of you are really good at using formulas, putting numbers in formulas. The hard part is setting up these problems. And so that's what I want to emphasize here today. When you work through problems, try to approach it in 4 steps. First one being draw a picture, visualize the problem. 2, identify the relevant principles or laws that you're going to need in order to analyze that problem. In the 3rd step, you're going to organize, rearrange those different laws in a way that allows you to solve for the unknown that is being asked for in your problem. And in the last step, I want you to substitute numbers. Okay? So problem 144, I'll read it. It says that the read-write head for a handheld music player has a surface area of 0.04 square millimeters. Okay, so the head is right here, and that head has an area of 0.04 square millimeters. The head is 0.04 micrometers above the disk, and the disk is rotating at a constant rate of 1800 RPMs. So you're being asked to figure out the torque that has to be applied to this disk in order to overcome the air resistance that occurs where the head meets the disk. And to help you visualize this better, I've got a disk here. Okay, so this disk is going to be spinning. We've got a read-write head, which is going to be sitting somewhere on the disk. And as that disk spins, okay, there's a small gap between the disk and the bottom of the head. And we can sketch that here. So here's the head, and here's the disk going by. So the disk is going to be going by at some speed v. We've got some head here, and then we're going to have a shear stress occurring right here in this space. And that shear stress acting on this area is going to create a force. Okay, and so when that force acts at some distance, that creates a torque. And that torque has to be overcome with this torque, okay? So on my diagram here, what I'm going to do is I'm going to say there is some kind of a force acting in this direction against the speed of rotation, okay? And that force is going to be acting a distance, we call it r, from the center of the disk. So one of the first principles I can write down to analyze this problem is that the torque that I'm being asked to solve for is going to be equal to the force due to this shear stress multiplied by this radius. Okay? Okay, what's another key idea here? Another key idea is going to be that we need to understand how this force is related to the fluid here. Okay, so if there is a shear stress inside this gap here, call that tau, and then the area over which this shear stress acts, we'll call that the area of the head. And the next relationship that I can write down is that the force due to shear stress will be equal to the shear stress times the area of the head. Okay? So we started off saying there's some force from this head acting at a distance r that gave me the torque. Now I'm saying, there's this little gap here where this disc is sliding by. It's creating shear stress in the fluid right here between the head and the disc. That shear stress, we'll call that tau. And that shear stress multiplied by an area gives me a force. And so that's the force listed here. The next thing I do is that I need to figure out how this shear stress is related to this velocity, okay? And to do that, we can use Newton's law of viscosity. Newton's law of viscosity says that the shear stress, I'll use blue, which shows up better. the shear stress in a fluid goes as the dynamic viscosity times the derivative u with respect to y. And so now if we look really closely here, we have the head, we have the disk going by, some velocity. So that means that inside this gap, the fluid velocity kind of looks like this, where it's moving fast, touching the disk at the bottom. At the top, it's stuck here. So the change in velocity with respect to distance would be equal to, it's going to be equal to the difference between this velocity and this velocity divided by this height. And so that will just be equal to the velocity of the disk divided by this thickness here. I'll call that h, okay? So now I can come down here and say that the shear stress must be equal to the dynamic viscosity of the fluid multiplied by v over h. Okay, now that I have these key relationships worked out, what I need to do now is rearrange them in order to solve for what's the problem is asking me to solve. So in this case, it's asking me to solve for the torque. And it looks like I need one more thing. I think in this problem, what's given here is the rotational rate here of the disk. So the other thing we know is that the velocity at this point, as it slides underneath, is just going to be equal to the angular velocity, omega, multiplied by the radius here, r. So draw this r a little bit darker so you can see what that represents. Okay, so that's the distance from the center of the disk to where the head is located on the disk. Okay, so these are the ideas that need to be assembled in order to solve this problem. So why don't we do that now? We put this expression into here, we put this one into here, we put this one into here, and then we have an expression for tau. Okay, so let's do that. We can start by saying that, take these two lines, combine this one, and we get the shear stress is going to be equal to mu times omega times r divided by h, okay? And if we put this expression into this expression, this tells us that the shear stress, this force due to the fluid shear, is going to be equal to mu times omega times r divided by h times the area of this the bottom of the head. And so now this I'm going to put into this expression, and I'll end up with the torque being equal to mu times omega times r divided by h times the area of the head. Okay, so at this point I have an analytical expression for the torque. Now I want to ask, does this make sense? Okay, so what this is telling me is that if the rotational speed of the disk increases, the torque will increase. Okay, that makes sense. The faster it goes, the more torque it's going to take to move it. Okay, I believe that. If the head is further out on the disk, it also means that the torque will increase. And that makes sense too, because the further out you go, the faster it goes, and also the bigger lever arm it has to create a torque. It says that the area of the head increases, then the force will increase, and that makes sense. A bigger surface area means a bigger area over which the stress acts and a bigger force. And then it says if the thickness, this gap height here, if that gets bigger, the stress will go down. Okay, so if this is getting bigger, that means that the gradient isn't quite as steep, and so that makes the torque smaller. So that makes sense as well. So now I have an analytical solution that makes sense to me. My last step is to substitute numbers. So I go back to my problem, and I say, what are the numbers I have? In this case, I know that the radius is 8 millimeters. I'm told that the head has an area of 0.04 square millimeters. So the area of the head is 0.04 millimeters squared. And I know that the gap height here, h, we're told is equal to 0.04 microns, 0.04 micrometers, so times 10 to the minus 6 meters. And the last thing we're told is that the air is at standard atmospheric pressure and a temperature of 20 degrees Celsius. So that information helps us get the viscosity of air. Okay? In order to do that, we go to the back of the book, and we pull up our table with fluid properties, properties of air versus altitude or pressure. So we don't, properties of air, it's different temperatures. Let's use this table. So we have at 20 degrees Celsius that the dynamic viscosity of air is equal to 18.1 times 10 to the minus 6. So we have 18.1 times 10 to the minus 6. And units are Newton seconds per meter squared. Okay, so now you have everything you need in order to work out the problem. Maybe one more thing to note here is that the rotational speed is given in revolutions per second. And omega is in radians per second, so remember to multiply by 2 pi to go from revolutions to radians. But if you put all those numbers in and work through the units, then you can solve for the torque. Okay? And I'll stop there.